Hi, my name is Pedro Fidalgo, and together with Christos Faloutsos and Mirela, we will present temporal graph mining for fraud detection. This tutorial will be split into three different parts. I will present the introduction to our work and the types of fraud we are dealing with. Christos will present part 2, graph mining patterns and tools, and finally Mirela will present part 3 with visualization and conclusions. Our structure in this presentation will always follow the same approach. We define and state the problem to be solved and provide a short answer and solution to it. We will then deep dive with more details and a long answer to it. Finally, we will provide the conclusions or a brief short answer as a resume. Graphs are everywhere. In the next slides, we will provide examples of each of these cases. In e-commerce, graphs optimize product connections and customer preferences, enhancing user experience. Moving to social networks, graphs underpin the complex web of online interactions and relationships. Concerning cybersecurity, we will examine how graphs are pivotal in detecting threats and securing networks. And lastly, in bioinformatics, graphs play a crucial role in understanding complex biological data and networks. In e-commerce, graphs offer invaluable insights into consumer behavior by mapping who buys what. They enable retailers to analyze purchasing patterns, linking customers with similar buying habits, and thereby tailoring market strategies to target specific consumer segments more effectively. But other graphs can be built from e-commerce. Who sells what, who reviews what, connecting products with sellers and customer reviews, offering insights into consumer satisfaction and influencing future purchasing decisions. In social networks, graphs map out the complex web of friendship, highlighting how individuals are interconnected and often revealing influential nodes or popular users within the network. This analysis not only helps in understanding social dynamics, but also in tailoring content and recommendations to enhance user engagement. The who friends whom aspect illustrates the direct connection between users, forming the fundamental structure of the network. Moving deeper, who follows whom, graphs shed light on one-way relationships, often signifying interest or influence dynamics. Lastly, who retweets whom provides insights into information flow and viral trends, highlighting how content and opinions propagate through these complex social webs. Graphs are one of the most important tools to map network topologies and understanding which machine connects to what. This visual representation allows for the detection of unusual patterns or anomalies in the network, indicating potential security breaches or threats. By analyzing these connections, cybersecurity experts can identify vulnerable points, monitor for unauthorized access, and bolster defense against sophisticated cyber attacks. In biomedicine, graphs provide a powerful tool to explain complex biological systems like protein-molecular interaction networks, drug and side effects, identifying adverse reactions, and finally correlate symptoms with potential disease, improving diagnostic accuracy. In a time-evolving graph, normal patterns represent typical expected behavior over time, providing a baseline for comparison. Suspicious patterns, on the other hand, deviate significantly from these norms, often signaling anomalies or emergent group behaviors that require further investigation to understand the causes and potential threats. I will show you real examples of each of these types of fraud to identify in the graphs, and the topics mentioned before also with criminal organizations. Specifically, we will show an example of each of these fraud types and suspicious networks. Brushing is a fraud where sellers send unsolicited or unwanted packages to random addresses, falsely inflate their sales volumes. This manipulation not only boosts the perceived popularity of products, but also creates fake customer reviews, skewing online marketplace integrity and misleading potential buyers. In social network fraud, the creation of fake Twitter followers represent a key tactic, where fraudsters boost their follower counts to falsely enhance their online presence or influence. This strategy not only misguides the public and potential sponsors, but also provide fraudsters with an unjust advantages, such as increased credibility and potential for lucrative commercial deals or political leverage. This can be easily purchased online, as you can see in this slide. One symptom of a potential fraud in social network is the lockstep behavior, where large groups of followers connect to the same group of followees, which is a significant pattern that indicates coordinated and unauthentic behavior. The dense area in the adjacent matrix reflects the two spikes on the right graph. In part 2, Christos will provide more details about it. If we think of a normal telecom subscriber, we will have a graph resembling a near click, forming some triangles belonging to a limited group of communities. Some fraud patterns create odd graphs, like bad telemarketers, robocalling, and 1GIRI. The first creates a star-shaped network full outbound, while the second creates an outbound star with some inbound edges. 1GIRI calls are made from very expensive numbers. They ring once and disconnect before the end user has the chance to answer the call. If the user tries to return the missed call, he will be charged a very expensive fee. Lastly, telephone denial of service, or TDOS. This is basically an extortion type of fraud, where fraudsters flood the destination number with calls to the point the victim will not be able to do or receive any calls. Typically, this is done to national emergency numbers or numbers that have a high dependency on phone lines. Fraudsters will only stop if the customer pays. Depending on the type of TDOS, this can be a star with a heavy weight on all edges or a node with the alt degree of 1 with a heavy weight. There are multiple types of fraud in telecom networks. Graphs are one of the key tools to identify them. The table on the right addresses a few examples and the graph features associated to them. In this case, we have the international revenue share fraud example, which is typically create a black hole, in other words, a full inbound star. Another characteristic of criminal and terrorist networks is that they try to cover their leaders and at the same time ensure resilience. One example comes from the 9/11 terrorist network, where the most central nodes, circled in red, are the leaders of the attack. Notice that any information to reach any part of the network have to pass through them. And at the same time, if a leaf, the most outside nodes, is caught, they won't be able to identify the leaders or any other important nodes. The same happens with this network, concerning the central nodes and the edge nodes. The nodes in purple reflect the leaders, central in line with the nodes circled in red, the road warriors, typically the ones that do the criminal work and more exposed to get caught. Notice the pattern of a full click connected to the rest of the network just by one node. They can be noticed in red. In this scenario, a fraud group was using compromised credit cards to top up the telecom subscriber plan for half of the fee. A leader, circling in red, was passing this information to the ringleaders, which would refill the plan of the subscriber. This graph is built with all nodes which were identified using compromised credit cards to refill their plan. The association between the fraudulent nodes, what we call a fraud ring, allowed us to understand the dynamic of the fraud networks with this type of characteristic. Bridge nodes with low degree, interconnecting hubs forming a star-bridge-star pattern. The influence of fraud nodes in the network is much higher than the non-fraudulent nodes, as you can see in the violin plot. Red nodes are associated with fraud, and gray nodes are not associated with fraud. Additionally, fraud nodes usually associate with control, showing some level of hierarchy. Now I will pass the presentation to Christos. Thank you all.
Welcome to the tutorial, the second part of the tutorial on graph mining for fraud detection. I'm Christos Faloutsos. And Pedro covered the first part, introduction and types of fraud. And what we'll cover in the second part are three subparts: static graphs unsupervised, static graphs semi-supervised, and time-evolving graphs. And then Mirela will cover the last two subsections. So let's start with static graphs unsupervised, blue background, and the bird stands for bird's eye view. So we'll see the problem of node importance. As we mentioned earlier, we'll follow a recipe structure. So for every problem, we'll have the problem definition with a question mark, and the background will be orange, right? Then we'll give the short answer with an icon of a key. Then we'll go over the details that you may want to skip on a first pass, and then we'll repeat the solution again at the end. So the problem we want to solve for this portion of the talk is node importance. We're given a graph like the one at the bottom, a directed graph. For example, web pages pointing to each other. We want to figure out two questions. The first question is which node is most important. The second question is how close is node A to node B. The short answer, the key icon, the short answer is there are two very good solutions for the node importance. The page rank, also known as PR, or RWR for random walk with restarts, and also the HITS algorithm, hubs and authorities algorithm, which is based on the singular value decomposition. Very, very powerful technique. The second question, the solution is the personalized page rank, PPR. As we mentioned, singular value decomposition is a very, very useful operation for graphs, which has all these properties. We won't go over these properties right now, but what we want to remember is whenever we have a matrix or a graph, SVD is a very good tool to help us find communities, find embeddings, find a lot of interesting things about the graph. So let's start with the first problem, node importance, and the very successful page rank algorithm. This is from based on work by Sergey Brin and Lawrence Page, who the founders of Google. And the idea is that when we have a graph and we want to find the most important node, the insight is that the node is important if the nodes that point to it, its parents, are also important. So this is a recursive definition which normally doesn't make sense, right? A cow is an animal whose mother is a cow. This is not a definition. But for the case of graphs, actually, this converges, as you might suspect, to a singular or eigenvalue. And what they proposed is the random surfer model. So this is a surfer and these are the waves. So the idea is that if we have a random surfer moving on the graph, nodes that have high steady state probability, SSP, are the ones whose parents have high steady state probability, and therefore the steady state probability of a random surfer indicates how important every node is. We're getting into details, but here is an arithmetic example. Suppose we have this graph where nodes point to each other. The adjacency matrix of this graph is not shown here, but if we do the transition matrix, which is adjacency matrix column normalized and transposed, this will tell us if we are on node 1, what are the chances we'll go to any other node? Well, if we're node 1, there is 100% chance we'll go to node 3. Oops. The other way around. This is from and to. So if we're starting from node 1, there are 100% chances we'll go to node 2, as it is shown here. So if we want to compute the steady state probabilities, which in this example will be a vector of 5 numbers, 5 columns, 5 rows, then the theory of Markov chain says that multiplying this matrix, the transition matrix, with the steady state probability should not change the steady state probability. That's the main insight, which means that this is the fixed point. The vector we want to find, the vector of importance we want to find, is the fixed point of this matrix vector multiplication. We'll skip the details. This is for the ones who want to do the implementation, right? And if we reveal the one that is hidden, scalar one that is hidden here, this is exactly the definition of the eigenvector of the matrix B with eigenvalue 1. It's a long story, but because the matrix is column normalized, then the first eigenvalue is 1. And this is exactly the definition of first eigenvalue and first eigenvector. There is a lot of very nice matrix algebra theory why this vector exists. This is the Perron-Frobenius theorem. The bottom line is that it exists, and this very intuitive mental picture of a surfer moving around on a graph gives exactly what we want, gives a steady state probability with high values for well-connected nodes, well-pointed to nodes. There is one important step in this algorithm. Occasionally, they allow for random jumps. So this simulates somebody who is surfing the web, goes around and then says, I'm bored, let me go to some other topic, right? But this random walk, this fly out, the random jumps have a very important mathematical significance. They make the matrix irreducible, and the Perron-Frobenius theorem we saw before applies, and we have a steady state. So what is happening here is a quick animation. Suppose we have this little toy graph, and the random surfer starts from the red dot here, flips a coin and says, should I teleport? Should I do the random jump? This is indicated by the parachute. The coin says no, continue. So then the random surfer says, I'll continue. I'll pick at random one of the two outgoing edges. So let's say we pick this one. So the random surfer moves here, flips again the fly out coin. Should I fly out? No, you should continue. Okay, how many choices I have? Only one. Okay, then follow that choice. That's it, right? Oops, sorry. Right. Follow the choice, and now it has to decide what to do again. Suppose now that the coin says, no, you should teleport. So the teleports and picks one of all these nodes at random and goes to that place. And this is an animation of the random surfer algorithm with restarts, random jumps, all teleportations. This is very well-known algorithm. This is the basis of Google, the initial algorithm that was used by Google initially. It is called the PageRank, random walk with restarts, or random surfer model. If we want to go into details, here's the mathematical operations. P is the vector of steady-state probabilities of importances. We want to know one entry for every column for every node of this graph. This is a scalar. This is the teleportation probability, 85%. And this is the identity matrix. This is the transition matrix that we mentioned before. We have to do an inversion, right? Or at least in theory, right? And what is important is that this vector is a vector full of ones. We will need this observation when we do the personalized PageRank later. So that's exactly it. The vector is full of ones. And notice that the PageRank is correlated within degree. If a lot of people point to a node, this node will probably have a high PageRank. And as we'll see later, the HITS algorithm also gives high scores to nodes with high in degree. Let's see how we can do the second problem, how we can do link prediction. The problem is, given a graph, things point to each other, web pages point to each other, or people retweet follow each other on Twitter, or retweet each other's tweets, right? How close is node A to node B? And the short answer, as we said, is the personalized PageRank, an award-winning paper by Taher Haweliwala, which says that the intuition is that a node, let's say node 4, is close to node 2 if there are a lot of paths that lead from node 2 to node 4. So here is a path. This is a reasonably short path. Here is another path. So the more paths we have, the shorter they are, and if it's a weighted graph, the heavier they are, then the closer node 4 is to node 2. How can we do that mathematically? It turns out we can do it extremely elegantly by having, instead of doing random flyouts, as the PageRank says, the flyout should be to our favorite node. So if the source node is node 2 here, every time we restart, we should restart from node 2. So the parachute now is not is tainted, is biased, and goes exactly, restarts at this node every time. Mathematically, this means that we could have exactly the same equation we had before. Yeah, we have to adjust a few things here, but the main idea is that this vector, instead of being full of ones, which means every node is equally probable as a restart target, we only have the desirable node as a restart target. And so this is very well understood, very easy to compute, right? And Network X, the Python package Network X computes it automatically, and this gives exactly the answer we want. This is not the only solution. There is the so-called escape probability, which the round trip probability and other variations. But even the plain personalized PageRank that we just described is a very good measure of how close is a node to another node. This is useful for recommendation, right? If this is a product shoes and this is product socks, right? People who like shoes, they tend to buy socks. So this is something that we would recommend. And they can also help with link prediction. So if this node is close to this node, according to the personalized PageRank, maybe Facebook would like to introduce them to each other and make them friends. There is also a very nice application, is the centerpiece subgraphs, which is part of the dissertation of Han Tong, now at University of Illinois Urbana-Champaign, right? So if we have a graph like that, and we have, let's say, these three nodes that are interesting, they are criminals or they are famous or something, and we want to figure out who is the center node, who is the person, the mastermind of this collection of criminals, then the centerpiece subgraph algorithm of Han Tong will figure out that this guy is the most important guy. So let's continue with node importance, and let's see the hits algorithm, which is the second extremely useful algorithm for finding importance. This is by John Kleinberg, now at Cornell, and this is one of the most highest cited papers in 1998. The problem, as you remember, is we are given a graph, directed graph, web pages pointing to each other, which is the most important node. Of course, you'll say, well, we already know PageRank and it's super successful, commercially very successful, right? Why do we need to discuss about yet another importance algorithm, right? For three reasons. The hits algorithm gives different scores, gives two scores for every node. How important is as it is as an authority, and how good a node is as a hub. If it points to good authorities, then it's a good hub. The hits algorithm can help us find the largest community, and the third reason is that hits eventually will lead to a very intuitive description of the singular value decomposition, which is a powerful tool and which can be extended to three modes, like time-evolving graphs that we'll see later, while PageRank cannot, or at least not easily. So remember, green background means we have seen it before, right? From PageRank, we have seen that the intuition behind PageRank is a node is important if its parents are important. The main insight behind the hubs and authorities algorithm of Kleinberg is that we would have two scores. A node will be judged as how important it is, and also will be judged as how wise it is. So a node is important if its parents or tutors or teachers are wise. A node is a good tutor or parent if its children are important. This is a relatively small distinction, but it makes a lot of sense, and it gives additional information for the graphs. So the Kleinberg algorithm says, suppose you want to find all the web pages that contain the word moussaka or something, some type of food. Find everything that has the word moussaka, and also all the pages, one step backward, all the pages that point to these blue pages, and all the pages that are being pointed to, even if they don't contain the word of interest. For the resulting graph, for the resulting subgraph, we want to give high score. We want to give two scores, an authority score for every node and a wisdom score or hubness score for every node too. How to do that? It's actually very intuitive, despite the fact that it leads to the powerful method, a very well-studied method of singular value decomposition. So green stands for wisdom, or of a teacher or a parent or a mentor, right? So node I will have the importance of node I, A sub I, is the sum of wisdom of the green dots of its parents. Makes a lot of sense, right? So we just add, in this case, the importance of node I will be 4, 1, 2, 3, 4, right? In matrix form, this is exactly how the authority vector will look like. We have 1 million nodes, so this vector will have 1 million entries of importance, right? This is the vector, 1 million vector, 1 million dimensional vector of hubness or wisdom scores, right? And this is the adjacency matrix transposed. Okay, but this is very intuitive. It makes sense. How do we compute how good the same node I, how good the node I is as a parent or as a teacher? Well, the Kleinberg suggested that we figure out what is the importance of its children, of its students, right? And then we add them all up, as the equation says, and this is the green score for node I. In this example, in this toy example, it's 1, 2, 3, 4, 5, 6, right? In matrix operation, this is that this means that the hubness scores or wisdom scores will be given by this matrix vector multiplication. And this is it. This is almost it. So Kleinberg suggested that we start with a random guess for the authority scores, multiply and figure out what are a good guess for the wisdom or hubness scores, put this vector there, multiply again with a transpose and figure out what is the improved authority scores, and then feed it back again, do it about a few times, 10, 20 times, and here is the surprising, the pleasant shock is that if we do a few times, then eventually this will lead to the left and right singular vectors of the adjacency matrix A. The definition of the singular vectors will come in a few slides, so stay tuned, but everybody agrees that this is a simple operation. Start with a random vector, multiply, 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 do that a few times, and this is it. And by matrix algebra, this will converge quickly after 10 iterations or so. It will converge quickly to the appropriate scores. And Kleinberg applied this algorithm. Back then, Java was a hot topic. And he applied to the query Java, and the most interesting websites were, of course, java.sun.com. Sun was bought by Oracle a few years ago, right? But back then it was the place for Java information, right? But also GameLand and Digital Focus were also very good websites because they had a lot of information about Java. And this is a place to stop and ask questions. And let me stop the recording for a moment. Welcome back. So we'll continue this presentation focusing on the singular value decomposition. We saw the PageRank and HITS algorithms, and now we'll see the properties of singular value decomposition. It has amazing properties. The first one is it can find hidden or latent variables. Let's go one after the other of these properties. So The mental picture we want to have for singular value decomposition is the following. Suppose we have a matrix of adjacency matrix of who follows whom, say on Twitter, right? And suppose that there are three groups of people. The green group, there are people who like music and the columns are famous musicians. The blue group, people who like sports and the columns are famous athletes. And the same for pink, concerned citizens, and the columns are famous politicians. Singular value decomposition of rank 3 will break this matrix into three pairs of vectors. And each of these pairs will correspond to one concept, correspond in the sense that if we do the outer product of these two vectors, u1 and v1, we'll get the green box. If we do the blue u2 versus v2 times v2 external product, we'll get the blue box and so on. And what is amazing is that the singular value decomposition will give us the right people, the music lovers, the music talent, the musicians, and so on. Even if the rows and columns are shuffled, in this toy example, the music fans are shuffled, but the U1 vector will have small values, 0 values for everybody else, except for the music lovers. And the U1 vector will have 0 everywhere except for the famous musicians, and similarly for the blue concept and the pink concept. But wait, there is more. Singular value decomposition will work even if there are a few missing edges from the full block, or if there are some additional edges. So this is called the salt and pepper noise. So this is salt, this is pepper, right? Even then, the singular value decomposition will get most of the music lovers will get high scores. Maybe there will be a few extras, right? And the same, most of the musicians will get high scores, and most of the rest will get very low scores. So, as we'll see later, 20 slides later, this is the basis for anomaly detection. And as we'll see 40, 50 slides later, it can be generalized to matrices of 3 modes, the so-called tensors, and like time-evolving graphs. So, the first property is that SVD can help us find hidden variables, the green concept, the blue concept, the pink concept. As we promised a few slides back, it can also help us compute the node importance, actually the hub and authority scores for every node. How? Remember, we promised that a few slides back. If we have the adjacency matrix of who follows whom, and if we do the rank 1 decomposition, we'll get the U1 vector, which will be the hubness scores, who are good parents or teachers, right? And the V1 vector, who are important nodes. So here we'll have famous musicians, and here we'll have people who are following the right famous people. So the authority scores is exactly the V1 vector. The hub scores are exactly the U1 vector. And this is what the HITS algorithm is doing. The third property is that SVD, singular value decomposition, can help us dense blocks in an adjacency matrix. We're more or less repeating what we said a few slides ago. So if there are clear blocks like the green, blue, and pink block, then the singular value decomposition will give us the pairs of vectors. Each pair of vectors will be able to reconstruct one of the blocks, the green block, by doing the outer product. Going down the list of properties, it can do dimensionality reduction. So suppose we have points. In this example, there are 2-dimensional points, in which case the matrix will have as many rows as points and as many columns as dimensions, 2 in this example, right? So if we do singular value decomposition of this matrix, the rank 1 decomposition will give us the V1 vector, which is the best vector to project these points, best in the sense of minimum root mean square error, which means the sum of squares of the green segments will be minimized if we project our black points on the V1 vector. If we want the second best vector, it will be V2, which will create a plane, the plane of V1 and V2, and so on and so forth. Finally, SVD can do embeddings. There's a lot of work on embeddings recently, the past 10 years. It turns out that if we have a shallow network, if we have an autoencoder which has linear units, so in this example, the autoencoder has only 3 internal units, only one layer, only one hidden layer. It's not a deep network, right? And it has linear transfer function. In that case, Apo Hivarinen and his co-authors, right, in the excellent book of independent component analysis, they show that the resulting embedding, if we have the L2 norm as the loss function, the resulting embedding is exactly the embedding of the singular value decomposition. So if we do SVD here, every fun, which is an m-dimensional vector, is represented by a 3-dimensional vector here. This will be exactly the 3 values that this row will correspond to after we do linear autoencoder. So SVD is a special case of a deep neural network. It's actually a shallow neural network with linear units. And this concludes the discussion of node importance. For spotting important nodes, we have 2 tools, PageRank and HITS, hubs and authorities. For guessing how close is node A to node B, we can use the personalized PageRank. This is, again, for the 4th time, the list of singular value decomposition properties. But the overarching message is that if we have a matrix or a graph, singular value decomposition is an excellent tool to start analyzing the graph. And now we will move to the next topic. How do we do community detection in a static graph? So the problem, orange background with a question mark, right? The problem is we're given a graph. The user wants us to create K communities. How can we write code to do that? In this toy example, the ideal algorithm should zap this edge, and we come up with 2 communities. It turns out that METIS by George Karipis and Vipin Kumar is an excellent algorithm to do that. The high-level idea of the METIS algorithm is that it does a coarsening of the graph, and then does the cut, and then does the uncoarsening. The algorithm is very mature. It's already since '98, and now the code is available, version 5. At the point of presentation, there is a website. There are publications with multiple variations and extensions of the basic algorithm. METIS is not the only solution. There is the Fiedler vector, which is related to the singular value decomposition, the modularity algorithm by Newman, Girvan, and Newman, and several other solutions, but the METIS is a good guess. A word of caution, though, is that even if we have an excellent algorithm for spotting communities, the graph might not have good cuts by construction. So here is the mental picture that all the books on matrix, the typical books on matrix algebra and sociology have. We assume that the matrix is block diagonal or close to that. In sociology, this is called the caveman graph, in the sense that all these prehistoric people were in the same cave and they know each other. These are people in the 2nd cave, and again they know each other. 3rd cave, and they know each other. If we have such a graph, maybe with a little bit of salt and pepper noise, if we have such a graph, any algorithm, any community detection algorithm will do a good job. However, a lot of real graphs don't have this structure. So here is a toy example. If we have a full click, it's not clear how to create 2 communities. People might say, well, this is not a realistic graph. That's probably true, but a reasonably realistic graph has a jellyfish shape, as published by Tauro and his colleagues, and followed up by George Siganos, right? So the jellyfish graph has a well-connected click. In this case, it was ISPs, internet service providers, that the big 11 ISPs, AT&T, Sprint, and so on, were very, very well connected. Each of them had a lot of customers. In the full jellyfish algorithm, there were additional layers, right? There was another circle of regional providers, but But even in this case, it's not clear how we could create a cut. We cannot cut here. We don't want to break AT&T from Sprint because they're all very well connected. We don't want to cut here because then we'll have a lot of disconnected customers, and this is not really a community, right? They are not connected with each other. In this paper, we show that a lot of other real graphs, like Google, parts of the web, and the similar graphs, they don't have good cuts. So the conclusion is that if we have a graph and we want to find communities, the METIS algorithm is the recommended one. But if the results don't make sense, it's not the fault of the algorithm, it's the fault of the data. There might not be good communities. And we can stop here for questions. Welcome back. We covered the singular value decomposition and community detection, and we'll continue with anomaly detection. So the problem is, given a graph like this one, we want to find two things. We want to find outliers, for example, a node like this one, which is probably a telemarketer in a phone network, right? And we want to find nodes that have lockstep behavior. Too many people, a subgraph where too many people doing exactly the same thing, because usually this is suspicious. And the solutions are many. We will go over two of them, the oddball algorithm and the singular value decomposition that we saw a few slides back. So, problem number one, given a graph, how do we find outliers? How do we find nodes that are strange? They have rare behavior. The meta question is, how do we start? What should we do? Probably there are many answers. There are infinite answers, actually. One very promising direction is to look at the egonet of every node. Egonet is everybody who's one step away from this node, and extract features. How many nodes are in the egonet, how many edges are in the egonet, and so on and so forth. So here are some egonets. This is a node, this is the egonet, all the neighbors, they are not connected. Here's another node, the egonet, a lot of neighbors not connected. Here is a third node, a toy example, right? It has 7, 8 neighbors, right? And some of them are connected, right? Here, this node has a lot of neighbors, and almost all of them are connected. They form triangles or quadruplets, right? So, how do we turn these subgraphs into a few numbers? And as we said, the features we can extract are literally infinite, and it's an art which features to extract. We can pick a few, and actually feature extraction is one of the hardest problems in machine learning, as was said in the applied data science panel in a few years back in KDD. So, which features would you pick? Well, the number of nodes makes sense. If this is an egonet, the number of nodes, the number of purple nodes makes sense. The number of edges in the egonet also makes sense. There are additional features mentioned in the oddball paper, but we won't elaborate here, because even these two features are good enough to help us spot outliers. Here is a real data set. This is the Enron data set, who mails whom in the Enron company. There was a big scandal in 2001 or 2002. And every node here is an account, Smith at Enron.com, Johnson at Enron.com, right? And the horizontal axis is the number of nodes in the egonet of Smith.com, Enron.com, right? And the vertical axis is the number of edges in the egonet. So logarithmic scales, because we expect power laws, right? And it turns out that a line of slope 1 usually seems to contain stars, while like this one. While nodes that are on a line of the blue line with slope almost 2 corresponds to nodes which are part of a big clique. Notice that most of the actual nodes are neither stars nor cliques. They're somewhere in between. A line fits reasonably well. A line with slope 1.3 fits reasonably well. On the average, every green point is the average of its neighbor of a bucket, right? And what is impressive is that this node here is far away from what it should be. Is an order of magnitude lower than it should be. It turns out that this node is the CEO of Enron, Kenneth Lay, who was convicted and eventually went to jail. But clearly, everybody would agree that this is an outlier. And so is this guy, which was, if I remember correctly, was the CFO, right? So these people had very strange behavior, very strange star-like behavior, while everybody else did not. So this is the tip of the iceberg on how to find outliers. Let's answer the second question. How do we find nodes who operate in lockstep? One would say, well, if people operate in lockstep, they will create blocks, as we had in this SVD mental picture, right? And blocks are normal, right? Actually wrong. We argued several slides ago that block diagonal matrices are actually not that frequent in practice. And Miguel Araujo, in his 2014 paper, in his dissertation, found that the typical real communities, they don't have a block structure, they have a boomerang structure, which more or less corresponds to the power law. This musician is famous, has a lot of followers. This musician is not very famous, has a few followers, right? This person likes all musicians, so follows all of them, right? This person is sort of half-hearted music lover, and this person likes only one musician. So boomerang communities are more natural. Okay, in that case, blocks are unnatural. So the question is, because blocks mean that all these people are doing exactly the same thing, which even intuitively makes no sense, right? If you have 1,000 people all following the same 200 musicians, that's very weird, right? So blocks are suspicious. How can we spot blocks quickly? This would be a puzzle, except that 15 slides ago, we said that SVD does exactly that. If there is a nice isolated block, it will find the members of this block, the rows and the columns of this block will be revealed by singular value decomposition. There are a lot of details. This is the mental picture that we mentioned before. Green means that we have seen this slide before. And as we said, if the adjacency matrix has 3 clear blocks, the rank 3 decomposition will find exactly these 3 blocks. We'll find the indicator vectors for the rows of these blocks and the columns for these blocks. We applied this idea on a paper with colleagues from Tsinghua and CMU. Some of you may recognize Peng Chui and Meng Jiang and Xikan Yang, professors now at Tsinghua and Notre Dame. That was a large data set from Tencent Weibo, 100 million nodes, 3 billion edges. When we did the singular value decomposition and we did a projection on the U1, U3 dimensions, right, we found some rays, spokes. And this means that all these people had more or less the same behavior. There were a lot of people at the 0-0 entry, which means they didn't participate in that behavior. And it turns out that rows that had a high score on the U3 vector, right, and the corresponding columns that had high score in the V3 vector, they formed a dense block. So here is the adjacency matrix of these followers and the corresponding followees, right? We were not able to dig much deeper, but when we plotted the degree distribution of a lot of nodes, there was a spike at 295 and another spike at 310. When we deleted these nodes, these edges between the suspicious followers and the suspicious followees, idols, these spikes disappeared, which means that they were organized. Somebody was paying or bribing or helping these people, forcing these people to follow, forcing all these people to follow all these people. So we can break here for questions. Let me stop recording. Welcome back. We'll continue with the third section of this presentation. We'll talk about static graphs and the semi-supervised case. The problem here is as follows. We have a graph like the one shown here, like the toy graph shown here, but now nodes have some labels. So we know that this has the red label, prefers the red color or votes for the red party, right? While this one prefers the green color or votes for the green party, right? And we're also given the compatibility matrix. Usually the compatibility matrix is homophily, so green people have green friends, red people have red friends, right? Sometimes we may have heterophily, the talkative people have silent friends and the other way around. The question is, how can we quickly figure out, given all this information, how can we quickly figure out what are the colors of the rest of the nodes, red or green? And the answer is belief propagation, and there are many versions of belief propagation, many implementations. We recommend the ZooBP, which is freely available from that website. So let's see, it's belief propagation is a very old method, very time-tested method. Here are some very nice introduction to it from Danai Kutra, professor at the University of Michigan. So the idea is, suppose we have a graph of co-authorship. So this is a person who is working on AI. This is a co-author of this person. This is a person who works on programming languages and their co-authors. And suppose we have a compatibility matrix. Red people, AI people have, in their vast majority have red co-authors, AI co-authors. Occasionally, rarely, they have a green co-author, right? So how can we find the colors of the rest? The idea is that every node sends messages to its neighbors, as shown in this animation. Oops. Okay, the animation didn't work. So after they send messages to each other, this node will say, I should be a little bit red because I'm connected to a red person. This node should be a little bit not that red, and these two people should be green because they are connected to a green person. That's the first round. The second round continues, and when it reaches a steady state, then we have the nodes, the node colors, right? Here are the assignment statements. So every message is the product of the state of the neighbors. So if all my neighbors are red, if my neighbor is red, sends me a red message. And here is how the messages are combined to create the belief of the ith node. So the ith node gets all the messages from its neighbors, Mij, right? And if all of them say you should be red, then this person tries to become red. This is good. This is from 2002, Yedidia, and earlier, right? And this is the end of the background. We'll see a fast approximation called FABP, and then eventually the ZooBP. As we mentioned, this is the paper that describes the linear approximation of BP. As we mentioned, the equation that Yedidia is proposing, the standard equations of belief propagation, are assignment statements. This is not a closed formula. We don't know. We cannot say anything about these equations, about these assignments. We don't even know if it will converge or not. So Danai, in her paper and her dissertation, was able to approximate these assignment statements with linear equations, which eventually become a matrix equation. So this is the identity matrix. This is the diagonal matrix of the degrees of the little graph that we have. This is the adjacency matrix of the graph we have. Clearly, we have 3 nodes in this toy example. Here are the initial beliefs of this of each node, 0, 10 to the minus 2, and so on. And here is the vector that we want to compute, the final beliefs, after all the messages, the Yedidia messages are passed, or the linearized versions. Notice that this is a closed formula. This is a matrix formula. We know when it will converge. It will converge when this matrix, the largest eigenvalue of this matrix, is less than 1. And based on that, she was able to apply it on several settings. However, we can generalize it even further for the case of heterogeneous graphs. For the fast BP that Danai developed works on a graph, on a homogeneous graph. Every node is of the same type, humans, every edge of the same type, connection, and we have only two labels, red and green. What happens if we have a heterogeneous graph with people, buyers? One type of nodes is buyers, another type of nodes is products, a third type of nodes is manufacturers. We have four types of edges, a thumbs up edge, a thumbs down edge. We have this person trusts this manufacturer, a plus edge. The black edge is which manufacturer manufactures what product, right? And suppose that we know that this is an honest person and this product is malware. What can we say about the rest? It turns out that using linear approximations, we can eventually turn the whole problem. Divya did a lot of very nice work here. We can eventually the problem can become a matrix equation. So this is a vector, this is a matrix, this is another matrix, right? Everything is known in this equation except for the belief scores. And I won't bore you with the details, but here is the application on some graphs. And here every dot is a node of a graph. The horizontal axis is the ZooBP score, whether this is honest or dishonest. The vertical axis is the standard, the Yedidia BP score. In an ideal setting, things would be along the 45-degree line. And yeah, this is the case. What is impressive is that the ZooBP of Divya is 600 times faster than the Yedidi algorithm implemented in MATLAB, both of them in MATLAB, and 3 times faster if both of them are implemented in C++. And here's the code that Divya has developed. So let's see some case studies. Belief propagation has been applied in many settings. We'll see 2 of them, one with an accounting setting with PwC, PricewaterhouseCoopers, and in malware detection with Symantec. So in the case of accounting, this is a published paper in KDD09. An accounting firm like PwC, its accountants have to check the client company within the first few weeks of January. So the accountants of PwC go to the company, take a look at all the accounts, the accounting books. Here is one account, here is another account. An edge means that there was a money transfer between these 2 accounts. Some accounts may look suspicious, may have too many round numbers or too many 9.99 amounts. So this makes them, there are some heuristics to make them suspicious. In this case, if the PwC employee has time to inspect only one account, which account should this person look at? This one, or which one? With belief propagation, the most suspicious account is this one because it is connected to a lot of suspicious accounts. So this algorithm saved a lot of time and also improved the accuracy of the investigations. The second case study was for Symantec, as we said, SDM 2011. The idea was Symantec has a database of a lot of machines which are using Symantec products and signatures of a lot of executables. So in this toy example, there is the Firefox. This machine has a copy of Firefox. This machine has a copy of Firefox and a copy of Microsoft Word. This machine has a copy of Firefox which is infected. Symantec knows that this copy is infected. What else could be infected? With belief propagation, the insight is that if this copy is infected, the sysadmin of this machine is not very careful. So there are chances that maybe this copy of Microsoft Word is also infected. So this is exactly the case of belief propagation. This is bad, this is suspicious, this might be also suspicious. So applying belief propagation there, Polo Chow was able to improve the TPR, true positive rate, by 2%, while the false positive rate remained the same. So that was a big gain for Symantec. So in conclusion, if we have semi-supervised case where we have labels for some of the nodes, red, green, or honest, dishonest, or fraud, or honest, right? And we know the compatibility matrix, we can propagate the labels and using belief propagation, or even better, linearized versions of it like FastBP or ZooBP. And we can stop here for questions. Welcome back to the last subsection. We'll talk about time-evolving graphs. So far we have been talking about static graphs, for example, who buys what. We have people buying products. This creates an adjacency matrix. If we have timestamps, like the example on the right, now we have who buys what and when, and this creates an adjacency matrix for every day or every hour, right? And the question is, how do we handle this collection of matrices? The answer, so that's exactly the problem. How do we find patterns and anomalies in a time-evolving graph? And the answer is, a very good starting point is the so-called parafact tensor decomposition. So let's see the details. We mentioned tensor. What exactly is a tensor? A tensor is a lot of matrices stacked together. For example, we have the adjacency matrix of which researcher publishes, uses what word in his or her publication. So John in KDD 19, in his papers, used the word data 13 times, the word mining 11 times, Peter 5 and 4 and 6 and so on, right? So that was KDD 2019. What about 20, similar matrix, 21, another matrix? If we put all these matrices one on top of the other, then this is exactly a tensor. And this is called a three-mode tensor because we have three sides: the researcher, the keyword, and the timestamp. Let's refresh our memory about singular value decomposition. Remember, if we have a two-mode matrix, which is a two-mode tensor, which is a matrix, and if this matrix has nice blocks, as we showed before, remember this is green background, we've seen this before, right? And we do decomposition of this matrix, SVD decomposition of this matrix, we'll get pairs of vectors, and every pair of vector will correspond to one of the hidden variables. So here are the musicians, or what do we say here, meat eaters and steaks, right? So here are the meat eaters who buy products from a supermarket. Here are the vegetarians who buy eggplants and lettuce and so on and so forth, right? It turns out that parafact generalizes this decomposition. So if we have a three-mode tensor, like a time-evolving graph, person, keyword, and time, or a knowledge-based subject, verb, object, right? And if there are nice boxes in this tensor, in this tensor, right? Then the parafact decomposition will give triplets of vectors, and every triplet will correspond to one of the topics. So suppose that one topic is politicians. So here is Biden is president of the US, Xi Jinping is prime minister of China, Justin Trudeau is prime minister of Canada. So here we have all the politicians, all the countries that they are leading, and all the locations, all their titles, president, prime minister, vice president, and so on. The next block here might have athletes and artists and what the group they play in, right? So here this Ringo Starr played in the Beatles, right? Played in the Beatles, and so on and so forth. And athletes, what team each athlete plays. So if we have nice boxes, the green, the blue, and the pink, then the parafact decomposition will give us one triplet for every such box. so it will find hidden variables the same way SVD finds hidden variables in two-mode matrices. There are a lot of details, of course, and we'll see the code. We'll give pointers to the code later. But let's see this applied in two settings. One is a phone call data set, and the other is a network traffic data set. So for the phone call data set, we had anonymized who calls whom data from a European country from a mobile carrier. So this mobile carrier had 4 million clients, each calling each other, and of course the carrier was recording all the phone calls, and they gave us data over 2 weeks, as we said, anonymized. If we do so clearly this is a three-mode tensor. Here is the caller, here is the callee, here is the time, right? The first, second, 14th day, right? We did the parafactor decomposition. The first few triplets were not very interesting, but the third or fourth triplet, if I remember correctly, was very interesting. So this vector had zeros everywhere except for one position. This is 4 million dots. If we squint here, this is a 4 and this is 10 to the 6, right? So there was only one caller who had a significant activity in this hidden variable. The second vector, the callees, there were out of the 4 million possibilities, there were only 5 people had a lot of activity, were receiving a lot of phone calls. And the third vector, the time vector, the 14-dimensional time vector, had zeros everywhere except for 4 days. So this was very weird because this person was calling these 5 receivers roughly 200 times a day, more or less with an equal count for these 5 receivers. So we didn't know how to make out of it. We called it the Godfather, calling its subordinates, right? The data was anonymized, so we were not able to figure out anything further. But it's definitely something that wouldn't show up without parafactor decomposition. The second example is network traffic, computer network traffic. So this is a public data set from the Lawrence Berkeley National Laboratory, and they recorded quadruplets of data. So it's a 4-mode tensor. It's a source IP, destination port, and timestamp. In this analysis, which was spearheaded by Evangelos Papalexakis, this person, in this analysis we ignored time, so we forced it to become a 3-mode tensor. And one of the hidden variables that we discovered had this weird property. There was only one source, only one destination, but there were a lot of destination ports. So this seems like either a port scanning attack, so this source were trying to figure out which of these ports is available, or a peer-to-peer file sharing setting where the source and the destination are jumping over several ports so that they don't get detected. And either way, it's something that stands out. Nobody else had similar behavior. So the conclusion for time-evolving graphs, how we find patterns in time-evolving graphs, is we can start with a parafactor tensor decomposition that we just mentioned. Here are the resources. NetworkX is a great Python package to analyze graphs. This is a Python package for tensor analysis, MATLAB package for tensor analysis. This is the dissertation from Danai Kutra, which contains all the information that we mentioned about belief propagation, FABP, and additional concepts. This is the monograph with Deepak Chakrabarty, which has a lot of patterns and anomalies for real graphs, static graphs, a survey by Lemana Koglu and also Danai Kutra on anomaly detection for graphs, papers on tensor decompositions. My thanks to Danai, Divi, and Vangelis, who allowed me to use some of their slides. And this is the end of this part. Mirela will take over and discuss about visualization, how to extract node features, and what visualization tools we can use to find anomalies in graphs. So this is the end of this presentation. Any questions?
Hi everyone. I'm Mirela Cazzolato, and I'm going to give the third and final part of our tutorial. So in this part of the talk, we're going to cover visualization tools and features for graph mining in a who calls whom and when network. So following the same structure that we have been seeing so far, we start with a brief problem definition. So in our case, we want to model a who calls whom network and when and for how long. And in this graph, we model millions of calls per day. Among these users in the network, we have honest customers and also fraudsters. Our main goal here is to find nodes with strange behavior. So for this, we take as input the source and destination numbers of a call, the timestamp, and also the call duration. We covered two cases in this modeling. We have the first one, which is the semi-supervised case, where we have very few labels previously provided by the network provider. And in the second case, we have no labels at all, which is the most common case here. And we want to find the fraudsters and explain why they are not honest. It's not enough here to point fingers. We need to convince the provider about them with some case building evidences. So a short answer of how we can model and deal with this problem. We have one standard approach here, which is we extract the node features from the graph, and this results in an n-dimensional feature vector. And we look for anomalies in these feature vectors, and we also plot different combinations of the extracted features in different and complementary ways. But how do we do all of that in a representative way is the long answer that we're going to explore a little bit more. So in this part, we're going to start with the feature structure so we can generate these n-dimensional vectors. The first question here is which features we should consider for extracting. And the straightforward answer is that we want the ones that help us to spot the types of fraud that we already know. So these types of frauds were covered in the first part of this tutorial. So for these types of fraud, we were able to map some node features that allowed us to map the fraudster's behavior here. So here we have the types of frauds that we've seen before. So we have brushing, where we can extract the degree, the velocity. We have telemarketers with all degree inter-arrival time, so they call very frequently, so the interval of these calls is very relevant here. Also, we have the 1 giddy that was mentioned before. We can take the duration of the calls and statistics from it, like median and variance. We have the DOS, so we can have some dense block detection using, for example, SVD, the coroners for detecting how well connected are these nodes. And we also have the lockstep and collusion types of fraud. So for these, we can use SVD, we can detect bridges and hubs. We can extract the incoming and outgoing calls to look for that. Okay, so specifically, we're looking at the possible features that we can and want to extract, how we can turn these nodes into n-dimensional vectors. We select those that are fast to compute, first of all, and also we excluded features that are like PageRank and triangles that are slow to extract. And also we want to extract here robust features to the application scenarios. So we rule out those average values and we consider instead median and interquartile range features. Okay. We also with these features that we selected, we are able to cover a few scenarios. For example, our features can inform us how well connected a node is. For example, with the coroners of each node, we can see how many distinct people called, how many calls were registered in our network, and the interval between calls and the call duration. And for these two categories, the interval and the call duration, we collect statistics like the median and interquartile ranges. And all of these we extract for both incoming and also outgoing calls. So with all of these features, we can perform a lot of tasks here. And for fraud detection, is a little bit obvious that we want to extract outliers from it, and we can do that. For this, we can use well-known tools like local outlier factor. We can use isolation forest. We can use Gen2Alt, which is from this work that we mentioned here. At the bottom, we can use many features in this context. But specifically, when we have lots of different fraud types in our network and very few labels or no labels at all, we want to spot strange behavior in our feature space, and that's obvious. But for that, we can work with different visualization tools, and that's what I'm going to talk in the next slides. So now we have these n-dimensional feature vectors, and our graph is very big. So for example, we can deal with 1 million nodes and 10 to 30 dimensions. So what are the options here to visualize these points? We came up with 5 main visualization tools. There are Spring Model, a JCC matrix, one-dimensional histograms, two-dimensional scatter plots, and also heat maps, and parallel coordinates. And we also provide a tool that is called tgraph Spot with all of these options for visualization. So the first visualization option for the Spring model, we can visualize, for example, an egonet of a set of selected points. And we can see how this egonet is composed with these selected nodes. From the egonet, we can generate the corresponding a JCC matrix, which is on the left here. And also for this option, we can generate the cross associations between these nodes, showing like dense blocks that might have in the network, for example, a lockstep behavior in our select data and so on. After that, we have one-dimensional histograms, and we can plot, for example, the call duration distribution here that we show in the slide. Also, we use log scale, which is important for the amount of data that we are dealing with. And in this case, specifically, we can see that we identified a behavior like this, where we can see clearly that there are a non-fraudster behavior, which is 2 for 1, comparing with fraudsters here. But at the end, we have a spike where we have fraudsters composing 50% of the calls in that spike, and this is very suspicious, and we took this case to the specialists as well. We also, from the different distributions of features, we can spot things like this. For example, here we have the fraudulent behavior causing a spike in the incoming call distribution. And this draws attention to the specialists, and we can see for this particular range of in degree what is strange there. And this is very meaningful for the application scenario. Using two-dimensional heat maps, we can see also in a log-log scale the examples of organized behavior like these, where we have a very similar median incoming call duration in this horizontal line. And we notice that the color here is also log scale, so we can work with these millions of subscribers in our network, and also being able to spot behaviors like that. Finally, with the parallel coordinates, we go from the 1- and 2-dimensional spaces to a d-dimensional space. And here we can visualize the behavior of selected nodes. Each line here is a node. And in this space, we can compose what we want to see. So the set of features that we want to see are features of interest. So we can select a set of features of interest and visualize the behavior of the nodes in these different features. And we have a recent tool, a recent work called tgraph Spot. And with all of these tools and visualization tools, we make it available in this GitHub repository. So we also have a demo video there if you're interested. So after that, we are going to see some case studies. So if anybody has questions, we can check them right now, or we can continue with the rest of the presentation. So let's see 2 examples of case studies that we have seen in previous analysis using our tools. In the first case study, we have a group of phone numbers receiving 1 second long calls. And in this case, we are checking the incoming calls related to the call durations and also the number of calls. So this is very suspicious. And after further inspection, we selected this black star from the set of numbers operating in a suspicious manner here. And the black star is a hotel, as we can see on the right here. And the hotel is connected with many confirmed fraudsters, and they are also very suspicious groups of numbers in this network that are connected with this hotel. And we wanted to check what is happening there, because we have confirmed fraudsters and also very suspicious groups in there. So the main question here is why people call hotel-like numbers for just 1 second. What's happening there? So in this scenario, we can have, for instance, people in Greece receiving these calls, just like our hotel. And people in the USA are calling people in Greece who stays at hotels. A shady, suspicious telecommunications company is used here, which controls the solid blue numbers in the slides. These telecom somehow charges lower rates, and in violation, this telecom somehow charges lower rates, and this is a violation to the regulations. But because of this telecom uses some substandard practices, many of these calls end up dropping, lasting 1 second only in the network. And this is why we can see a group of numbers with 1 second median duration in there. So in the second case study that we have this horizontal line here, a group that we selected because they are receiving calls with very similar median duration. So we selected one of these numbers, the red star, and we saw that for this number, this number was receiving lots of calls during sleeping hours, with a sum of high incoming duration. So this is very suspicious. Why would these numbers receive lots of calls during sleeping hours, and the sum of these durations is very high for these lots of times in the day, okay, these periods. So after we saw these selected numbers, that group that is very suspicious, we saw that the calls have median call duration between 10 to 15 seconds, which is very suspicious for us. And after the anonymization, we found out that these numbers are information numbers like weather forecast and stock market numbers. So the question here is, why would somebody call information numbers 10 seconds at a time during sleeping hours? So the answer is camouflage. So these callers, they have a lot of shady international traffic as well. And these calls have automatic answers. So for camouflage, they give fraudsters call duration to camouflage their high amount of calls, also from these numbers that won't respond. So they would call lots of times for numbers that won't respond. And to camouflage this behavior, they call these automatic numbers that have automatic messages and give them some duration to camouflage themselves in the behavior of the network. So this behavior helps them evade filters that aim to detect these activities in the network. So these are 2 real cases that we are able to detect with our tools. Okay, so just to conclude our presentation now, we have some excellent tools for static graphs time evolving and heterogeneous graphs here. We show many tools for both visualization and explanations. And we also have the need here that is vital for specialists for case building and understanding. It's not enough to say to them that I know that a number, that a subscriber is a fraudster. We need to explain why. And we finish our tutorial here. Thank you everyone for attending, and we are open for questions. Thank you.